Welcome to the Deep Dive, where we peel back the layers of seemingly ordinary subjects to reveal their extraordinary impact and their often surprising journey through history and into the future. Today, we're plunging into a material you interact with every single day, perhaps without a second thought. Concrete. It's the silent, unsung hero under our feet, surrounding us in our homes and cities, a material with a legacy that spans millennia. We're going to explore a really critical question today. How can this incredibly essential building material, the very foundation of our built world, adapt and evolve to meet the monumental environmental challenges of the 21st century? This isn't just an academic look at a construction material, it's a fascinating journey from the ancient, almost magical recipes of antiquity to the cutting-edge innovations emerging from modern material science. It's a genuinely hopeful deep dive into how we're reinventing a technology that's been with us for over 2,000 years.
You've hit on such an important point there. Concrete truly is indispensable. If you just pause for a moment and look around you, you'll see it everywhere. The roads we drive on, the bridges that connect us, the foundations of our homes, the walls of our buildings, even the very sidewalks beneath our feet. It's foundational, really, to nearly every structure around us. But this very ubiquity, this absolute reliance we have on it, means its environmental footprint is immense, and therefore something we simply cannot afford to ignore any longer. This deep dive will take us back to concrete's astonishing origins, meticulously trace the current challenges posed by its massive scale production, and then illuminate the groundbreaking research and development efforts aimed at forging a much more sustainable future for this ancient material. And importantly, we'll explore not just revolutionary new material compositions, but also how ingenious design principles and powerful digital tools are radically transforming its use. The goal: to create optimized structures that inherently require far less material, drastically shrinking that environmental impact.
Okay, great. So let's start at the beginning then. All right, let's pull back the curtain on this. Before we project into concrete's future, we absolutely have to pause and truly marvel at its incredible past. This isn't some recent innovation born of the industrial age. It's a technology that boasts roots deep in antiquity, embodying an ingenuity from ancient builders that frankly continues to impress and even astound us today. The sheer longevity of some of these structures is almost baffling.
Absolutely. When you think about enduring engineering, the Roman Empire immediately comes to mind, doesn't it? They weren't just conquerors, they were master builders.
Yeah.
And their structures have literally stood the test of time, often for 2 millennia or more, defying earthquakes, wars, and the relentless march of weather. It's quite something.
Take the Pont du Gard, for instance. That magnificent Roman aqueduct in Nîmes, France, built way back in the 1st century BC. It isn't merely a marvel of hydraulic engineering. It's a profound testament to the inherent strength of the materials they used and the builders' almost uncanny understanding of structural principles. Its arches still stand proudly today, a silent monument to their foresight.
Right. The sheer scale, the elegance, and the survival of structures like that truly underscore the enduring quality of their concrete and the sophisticated knowledge that underpinned its application. They weren't just mixing ingredients haphazardly. They had an empirical, almost scientific approach to it, even back then.
And what's truly remarkable is that we have insights into their methods thanks to incredible historical records. Like, we can actually look this stuff up. We can delve into Vitruvius's seminal work, 10 books on architecture, a foundational text from that era, which acts like a construction manual from the ancient world.
Exactly. And within its pages, we uncover surprisingly detailed recipes for ancient lime mortar. Vitruvius, writing around 25 BC, he meticulously explained the importance of the stone used for lime. He specified that it should ideally be white, whether soft or hard. He wasn't just being prescriptive. He understood material properties.
So he knew different stones worked better for different things.
Precisely. For instance, he recommended hard, close-grained stone for structural parts, recognizing its superior compressive strength, while suggesting more porous stone for stucco, where workability and breathability were more crucial. This demonstrates a clear, nuanced understanding of how to match materials to specific applications. That's a principle that remains fundamental in civil engineering today.
Okay, that makes sense. But his precision didn't stop there, did it? You mentioned recipes.
Not at all. He also gave remarkably precise missing proportions for different types of sand, which is genuinely fascinating when you dig into it. For pit sand, which is often coarser and well-drained, he advised 3 parts sand to 1 part lime. However, for river or sea sand, which tended to be finer, more rounded, and sometimes contained impurities, the ratio shifted to 2 parts sand to 1 part lime. He was clearly acknowledging their differing properties and the need for a stronger binder concentration.
So he's adjusting the mix based on the aggregate. That's pretty sophisticated.
It really is. But here's where it truly gets intriguing, offering a direct parallel to modern material science. Vitruvius recommended the addition of a third part of burnt brick, pounded up and sifted.
Burnt brick, like old bricks ground up.
Exactly. And specifically when using river or sea sand for mortar. This wasn't merely an arbitrary filler, it was a deliberate material modification intended to improve the mortar's composition. It enhanced its hydraulic properties, basically, its ability to set and harden, even underwater, and its overall performance, especially in damp conditions where sea sand might be used.
Wow. So they were basically adding performance enhancers 2,000 years ago.
You can definitely say that. Conceptually, this ancient practice of adding finely ground burnt brick to their line-based binder is seen by many as a precursor to modern supplementary cementitious materials, or SCMs. We today add finely ground materials like fly ash from coal power plants or slag from steel manufacturing to Portland cement.
Right, I've heard of fly ash.
Yeah, and we do it to improve its properties, reduce the amount of pure cement needed, and significantly lessen its environmental impact. The Romans were, in essence, innovating with binders 2 millennia ago.
That Roman ingenuity, particularly their understanding of how to modify mortar, is absolutely a central takeaway then. It's amazing.
It really is. If we connect this to the bigger picture, it becomes clear that the Romans weren't just intuitively mixing sand and lime, they were actively engaged in what we would unequivocally call material science. They had an incredibly sophisticated, albeit empirical, based on observation and experience understanding of how different aggregates and, crucially, how various additives like that burnt brick could dramatically impact the durability, strength, and overall performance of their construction materials.
So it wasn't just luck that their buildings lasted so long.
Not at all. This deep, practical knowledge, accumulated over generations, allowed them to build structures that have outlasted empires. It's a testament to ancient R&D, if you will, a profound understanding that we are now, with our advanced tools and scientific methods, in many ways rediscovering, refining, and reinventing.
And this mastery let them build huge structures, right?
Absolutely. This mastery of their unique concrete allowed for the construction of monumental and incredibly complex structures that showcased engineering brilliance. Think of the Theater of Marcellus or the mighty Colosseum, both of which utilize what's known as engaged orders. As described by Viollet-le-Duc, these weren't merely decorative columns or pilasters, they acted as essential buttresses, distributing immense loads and ensuring the structural integrity of these massive multi-story buildings.
Ah, so the columns weren't just for sure, they were part of the structure itself.
Exactly. Such sophisticated application of engineering principles would have been utterly impossible without the unparalleled strength and lasting power of their meticulously formulated concrete. It's a powerful illustration of material science directly enabling architectural ambition.
It's a stunning parallel, isn't it? That a 2,000-year-old blueprint could lay the groundwork for modern material science. It truly makes you wonder how much lost knowledge we're still rediscovering. And yet, for all that ancient ingenuity, concrete's role today is even more pervasive, underpinning almost everything we see, truly a testament to its incredible versatility and foundational strength. Let's fast forward to its current dominion.
Right, so bringing it to the modern day.
Today, concrete remains the ubiquitous building block of our modern world, and its applications are vast and diverse, touching almost every aspect of our built environment. Our sources detail this extensively. Consider deep foundations, for instance. We often take them for granted, but imagine a towering skyscraper in a bustling city built on soft, unstable ground, places where the soil isn't great.
Yeah, like landfill or marshy area.
Exactly. Concrete piles become the literal backbone of such structures, drilled hundreds of feet deep, sometimes even to bedrock, to transfer colossal building loads safely through unsuitable soil strata.
It's a silent, unseen battle against gravity and geology, where concrete's immense compressive strength and durability are absolutely non-negotiable. It has to work.
Beyond these subterranean giants, concrete forms our robust foundation walls, anchoring our homes and buildings firmly to the earth. It gives us the precise, standardized components of concrete masonry unit cinder blocks, basically allowing for modular construction.
Very common.
We rely on it for the immense strength of piles and the unwavering stability of retaining walls that hold back hillsides and prevent erosion. Look up and you'll find concrete roof slabs and floor systems providing expansive, fire-resistant spans. Look down and you'll walk on durable concrete slabs on grade in our basements and garages, even everyday elements like stairs.
Sure.
The lintels that span openings in masonry walls and reinforced concrete pie beams, those critical, often unseen elements that link column footings to prevent differential settlement, particularly important in challenging soil conditions or active seismic zones, all rely on concrete.
Its sheer adaptability means it underpins virtually every type of construction, from the simplest shed to the most complex high-rise. It's just everywhere.
But concrete's role truly extends far beyond just basic structure. It's also absolutely vital for performance and protection, particularly when it comes to safety in our buildings.
Right, fire resistance is a big one.
Exactly. Our sources prominently highlight its crucial role in providing fire protection. They note that concrete, especially when formulated with lightweight aggregate, is inherently inflammable and possesses a remarkable ability to withstand extremely high temperatures without disintegrating. This intrinsic property makes it a preferred and often mandated material for creating fire resistance rated structural elements as detailed in building codes, which set stringent requirements for how long different building components must resist fire.
It buys time for people to get out safely. That's critical.
It really is. It's a silent guardian, buying precious time. And beyond these critical structural and safety applications, concrete takes on more traditional, yet still widely prevalent forms. We see it as Portland cement plaster stucco, a common exterior finish offering durability and aesthetic appeal.
Yeah, you see stucco everywhere, especially in certain climates.
And we even find specialized materials like keen cement, which is a type of plaster that achieves a very hard, smooth surface.
So lots of variety even within the standard stuff.
Exactly. These examples collectively demonstrate the incredible variety and specialization that exists even within conventional cementitious materials, all stemming from that ancient understanding of how to tailor mixes for specific needs. It's truly remarkable how a material with such ancient roots continues to be so fundamental to our modern safety and structural needs.
Okay, so we've established concrete's ancient genius and its modern ubiquity. It truly is the workhorse of our built environment, foundational to so much. But here's the uncomfortable truth, the elephant in the room, really. For all its strengths and incredible utility, our current dependence on concrete, especially traditional Portland cement, also represents one of the biggest environmental dilemmas of our age.
Right. It's a classic Faustian bargain, isn't it? Immense utility, but with a massive looming cost for our planet. That 8% of global CO2 emissions figure is just staggering when you think about it.
It really is. And Samuel Florman, in The Existential Pleasures of Engineering, kind of frames this broader concept. Technology, while enabling us to achieve incredible feats, can also perhaps inadvertently lead us to the brink of disaster, necessitating an abrupt change, of course. When we apply this philosophical lens to the massive scale of concrete production, today we're talking about billions of tons annually, the most consumed material on Earth after water, the urine sea, and urgency becomes startlingly clear.
Billions of tons. It's hard to even picture that amount.
Exactly. The production of Portland cement, the key binder ingredient in most concrete, is notoriously energy intensive. It requires heating limestone and other materials in massive kilns to incredibly high temperatures, around 1450 degrees Celsius.
And that process releases huge amounts of CO2, both from the chemical reactions and the burning of fossil fuels for the heat.
Precisely. That's where that 8% figure comes from. So the challenge isn't just about finding niche alternatives, it's about initiating a systemic, industry-wide shift in how we approach construction. It aligns with the idea from thinking in systems that systems can't be controlled, but they can be designed and redesigned. We're talking about reforming an entire colossal industry from the ground up to reduce its carbon footprint.
The scale of the problem is truly global, demanding a global response. It feels overwhelming sometimes.
It can, but there's a powerful and extremely positive trend already in full swing that offers real hope: the rapid and undeniable rise of green building. Our source, Sustainable Construction Green Building Design and Delivery, provides compelling statistics that illustrate this profound market shift.
Yeah, those numbers were pretty striking.
They really are. Consider this. In 2005, a mere 2% of non-residential new construction was classified as green. By 2010, that figure didn't just inch up, it surged dramatically to between 28% and 35%.
Wow, that's a huge jump in just 5 years.
It is. And by 2015, just a decade after green building was a niche concept, it was estimated to reach an astonishing 40% to 48% of all new non-residential projects. This isn't just a fleeting trend or a feel-good initiative. It represents a multi-billion-dollar economic force, directly supporting millions of jobs in the U.S. economy alone.
So sustainability is becoming profitable. It's becoming the standard.
Exactly. It's a powerful signal screaming that sustainability is profitability, that environmentally responsible construction is rapidly becoming the industry standard, reshaping an entire sector faster than almost anyone could have predicted. It demonstrates a clear market demand and a societal imperative for more sustainable approaches in construction, which is exactly the kind of momentum needed to tackle the concrete problem.
Okay, so the market is demanding change. That's good news. But how do we actually do it? How do we make concrete greener?
That market shift isn't just a ripple, it's a tidal wave, signaling a profound reevaluation of priorities within the construction industry. But the real challenge, as you hinted at, isn't just wanting to be green. It's how we actually make one of our most fundamental materials, concrete, truly sustainable, especially given the sheer volume of it that we consume globally. This brings us to a crucial concept, dematerialization. Our sustainable construction source champions this approach, which is essentially about using the absolute minimal amount of materials required to achieve a building's function.
Using less stuff, basically. Makes sense.
It's a deceptively simple idea, but incredibly powerful. If you use less of anything, you inherently reduce its environmental impact, from extraction and manufacturing to transportation and waste. This approach inherently lowers the demand for products manufactured from virgin resources, thereby cutting energy consumption and associated emissions across the entire supply chain. Less concrete means less cement, means less CO2.
So how do we dematerialize in practice? What does that look like?
Well, a straightforward yet highly effective example cited in our sources is rejecting floor finishes in favor of finished concrete.
So polishing the concrete slab instead of putting carpet or tile over it.
Exactly. Instead of layering additional materials like carpet, ceramic tile, or hardwood flooring on top of a structural concrete slab, designers are increasingly choosing to polish, stain, or simply seal the concrete itself to serve as the final floor surface. This simple decision directly eliminates the material consumption and associated impacts of manufacturing, transporting, and installing those secondary finishes.
Okay, I can see that. Simple but effective.
It embodies a clear principle: use less, achieve more. It's about leveraging the inherent properties of the primary structural material. Furthermore, our thinking needs to extend beyond just the initial construction phase to encompass the entire life cycle of buildings. That's where design for deconstruction, or DFD, comes into play.
Design for deconstruction.
Right.
Planning for the end at the beginning.
Precisely. DFD is a proactive strategy to modify existing building designs so that they incorporate design for deconstruction, DFD, as a component of the overall building design strategy, and by using materials that will have future value for recycling. This means consciously designing buildings not just for their primary use, but also for their eventual end of life. It involves selecting materials that can be easily disassembled, recovered, and either reused directly or recycled into new products, rather than simply ending up in a landfill.
So instead of a wrecking ball, you can take the building apart piece by piece.
That's the idea. Imagine designing a concrete wall, not as a monolithic, impossible to separate structure, but perhaps as modular precast panels that can be unbolted and repurposed. This closes the loop on material flows, ensuring that the resources we embed in our buildings today can remain valuable assets for future generations. This holistic approach, from minimal material use to maximum recovery and recycling, is absolutely crucial for building a truly sustainable future.
That sounds incredibly logical, designing for the end from the beginning. It completely reframes how we think about a building's life. But, realistically, in the often conservative and budget-driven world of construction, where margins are tight, how much real appetite is there for DFD? Does it add significant upfront costs, and how do we overcome that inertia?
That's a very valid point. There can be perceived upfront costs, or at least changes to established practices, which always face some resistance. But the long-term value proposition, easier maintenance, adaptability, and resource recovery, is starting to gain traction. Plus, the drive for efficiency isn't just about what we build with or even end-of-life planning. It's fundamentally changing how we design and construct it. And that's where digital tools are really shaking things up.
You're absolutely right. Digital tools are transforming everything. One of the most exciting frontiers for dramatically reducing material use and optimizing construction isn't solely about the concrete material itself, but how we conceptualize, design, and ultimately build with it. We're talking about truly revolutionary digital tools and processes that are driving massive leaps in efficiency. It's not just drawing anymore.
Not at all. So let's dive into building information modeling, or BIM. The BIM handbook explains BIM as much more than just 3D modeling software. It describes BIM applications across three crucial levels: as sophisticated tools, as integrated platforms, and as collaborative environments. The overarching goal behind BIM is twofold: achieving project synchronization, getting everyone on the same page, and ensuring unwavering model integrity throughout the entire lifecycle of a project.
So it's like a central digital hub for the entire project.
Exactly. BIM fundamentally changes how designers, engineers, and contractors, indeed all stakeholders, work together. It facilitates unprecedented interoperability, allowing for seamless, intelligent data exchanges between a central BIM platform and a vast array of specialized analysis tools. Imagine being able to feed your architectural model directly into structural analysis software to check loads and stresses, or into a thermal analysis tool to optimize energy performance, or even into applications for precise quantity takeoffs and dynamic scheduling.
So the different software can actually talk to each other through the BIM model.
Yes, that's the key. This level of integration means that specific portions of the platform's native data model are intelligently transloaded and shared across disciplines, making the entire design and construction process vastly more efficient, reducing errors, and critically, enabling a much deeper level of optimization.
And this leads us to where it truly gets mind-blowing. Parametric modeling within BIM. Can you explain what that means?
Sure. Parametric modeling offers immense advantages for tackling complex geometries, think curvy buildings or intricate structures, and fostering real-time collaboration. Our sources explain that it drastically slashes the time needed for calculations that would be prohibitively time-consuming and prone to human error with traditional manual input methods.
Give us an example.
Okay, consider the challenge of designing a stadium with a complex, doubly curved envelope geometry and its intricate supporting truss system. In the old days, every time the architect tweaked even a small curve or angle, engineers would have to manually recalculate every single truss element, every beam, every load path.
Which sounds like a nightmare.
It was a grueling process that could literally take weeks, halting progress and adding immense cost. Parametric modeling obliterates this bottleneck. You don't define just fixed positions, you define the relationships between all the elements. So when the architect adjusts that curve, the entire structural model automatically adapts, recalculates all the stresses and material requirements, and provides instant feedback.
Wow. Automatic recalculations.
Exactly. Our sources give a vivid example. Custom integration of parametric modeling and structural analysis allowed engineers to generate an entire set of 51 loading scenarios ready for analysis, with no need for manual intervention. Think about it, 51 scenarios calculated instantly. This drastic acceleration of the design analysis feedback cycle directly leads to highly optimized designs that inherently use significantly less material, because every component can be precisely engineered for its exact load and function, eliminating unnecessary overdesign or fat in the structure.
It's like having a super intelligent assistant constantly doing complex math in the background, allowing for rapid iteration and pinpoint optimization. That's a game changer for efficiency.
Absolutely. Building seamlessly on the capabilities of BIM, we have virtual design and construction, or VDC.
Okay, another acronym, VDC.
Right. Construction Management Jumpstart provides a clear definition. VDC is the act of visually assessing, analyzing, and managing all work on a construction project in a 3D virtual environment before building the project and performing any work on site.
So you build the whole thing digitally first.
Essentially, yes. This isn't just visualization. It's a profound shift towards digitally constructing the entire project before you ever lay a single brick or pour a yard of concrete in the physical world. The immediate benefits are incredibly profound. Design and construction teams, working collaboratively across disciplines, can plan, design, coordinate, and construct a project virtually, identifying and resolving potential clashes, optimizing material usage, and refining construction sequences long before any physical work commences.
Finding problems before they happen on site must save a lot of time and money.
Immense amounts of time, money, and materials, preventing costly rework. Crucially, BIM makes it possible to determine impacts in real time. As design features within the model are adjusted, so will the estimates in the schedule. This instantaneous feedback loop is precisely what directly leads to optimized structures that use far less material, by identifying inefficiencies and enabling precise material reductions pre-construction. This capability is a genuine game changer for sustainability, transforming how we approach building from conception to completion.
What's truly fascinating here is that this isn't merely about generating visually appealing 3D models or pretty pictures. It represents a fundamental paradigm-shifting transformation from traditional manual, sequential, and often siloed processes to a deeply integrated data-driven design and construction workflow.
Right. BIM and VDC empower us to simulate, optimize, and foresee potential issues and opportunities with an unprecedented level of precision and foresight. This capability directly translates to significant material savings, dramatically reduced waste on-site, and a substantial enhancement in overall project efficiency and predictability.
But are we using it to its full potential yet?
Well, while establishing design intent and automating design documents is a very common and valuable use of BIM today, our sources rightly point out that we have barely scratched the surface regarding the BIM's capabilities and usefulness. Think about it. Even though we could be loading these digital models with actual manufacturer's objects, each linked to full product data sheets containing detailed specifications, environmental impact data, and even pricing, we often still rely on generic objects without that crucial, granular information.
So we could be making even smarter choices based on real product data.
Exactly. Maximizing the data richness within these models offers an even greater, largely untapped potential for optimization, allowing us to choose materials not just for cost or performance, but for their carbon footprint and recyclability, life cycle impacts, everything.
That brings us to a really critical, often overlooked aspect, BIM execution planning. Sounds important.
It is. With so many diverse team members, from architects and structural engineers to HVAC specialists, plumbers, construction managers, and even future operations and facilities personnel, all relying on the BIM model to plan, coordinate, and execute their work, a tremendous amount of upfront strategic planning is essential for how the model itself will be developed and used. It's the responsibility of the Virtual Design and Construction (VDC) team, in close collaboration with the project owner, to meticulously define the extent to which the model should be developed to best serve all parties' expectations and needs throughout the building's entire life cycle.
So everyone needs to agree on how detailed the model needs to be and for what purpose.
Precisely. A pivotal part of this process involves all stakeholders understanding the distinct differences between, for example, a design intent model, which focuses on aesthetic and spatial concepts, a construction model, which details constructability and sequencing, and a facilities management model, which will contain data crucial for ongoing maintenance, energy management, and future renovations. Knowing how the digital twin of the building will be used from its initial concept all the way through its operational life and eventual deconstruction is fundamental to effective BIM execution planning. It ensures that the technology serves all its purposes efficiently and effectively, and crucially, always contributing to that overarching goal of creating optimized structures with far less material.
That's a powerful point, truly understanding the life cycle of the digital model. It sounds like a sophisticated dance of data and collaboration. But, hearing about this incredible digital capability, it makes me think about something else. The future isn't just about centralized, large-scale construction managed by these complex digital twins. It's also about democratizing manufacturing and localizing innovation, empowering communities to build smarter and more sustainably, often on a much more accessible scale. This is a profound shift, don't you think?
Oh, absolutely. It's a massive shift. It's moving some of that power and capability outwards. Let's talk about a fascinating example of this decentralization, the Fab Lab movement.
Fab Labs, right? I've heard of those. Fabrication laboratories.
Exactly. This incredible program, which originated at MIT back in 2001, has blossomed into a sprawling worldwide network of local fabrication facilities. The vision, as articulated by its founder, Neil Gershenfeld, was refreshingly simple yet profoundly impactful. Instead of talking about it, I'd give people the tools. The real opportunity is to harness the inventive power of the world to locally design and produce solutions to local problems.
So giving people access to tools like 3D printers and laser cutters.
Precisely. It's about empowering individuals and communities with access to advanced digital fabrication tools. Imagine, as our resources suggest, shepherds in a remote village in Norway using a local fab lab to design and create custom radio frequency ID tags for tracking their wandering sheep.
That's a great example, using high-tech tools for a very practical local problem.
It's a perfect, tangible example of local innovation solving a local need, enabled by global access to cutting-edge technology. This very idea of localized digital fabrication connects directly to producing optimized structures that use far less material by allowing for precise, on-demand manufacturing of components, tailored design solutions for specific environmental contexts, and a significant reduction in waste and the environmental impact associated with long-distance transportation of materials. It's truly a bottom-up revolution in making things.
Taking this concept of open innovation a step further, we arrive at the idea of hackable cities. Sounds intriguing. What does that mean?
Well, our sources delve into the notion of making urban systems and infrastructure more hackable, not in the sense of malicious intrusion, obviously, but by opening up platforms and data for urban information. This fosters what we call appropriation and experimentation by city residents.
Meaning people can use city data and platforms to create their own solutions.
Exactly. It means empowering citizens, urban planners, and local businesses to creatively engage with their urban environment, to identify problems, and then design and implement innovative solutions using available tools and data. Imagine a neighborhood identifying a need for more shaded public spaces. Instead of waiting for a monolithic city project, local fab labs could be used to design and prototype modular, sustainable shade structures, perhaps even using recycled or locally sourced concrete forms or other materials.
So it encourages grassroots innovation within the city itself.
Yes, this promotes a groundswell of widespread, grassroots innovations in construction and material use, tailored specifically to local needs and resources, fostering a culture of continuous improvement and sustainability right from the neighborhood level. It's about making cities more responsive and resilient through citizen-led ingenuity.
This philosophy then expands into the broader, incredibly ambitious Fab City vision. What's the big goal there?
It's an aspirational goal, powerfully articulated in Designing Reality, which poses a compelling question. What if our cities could be globally connected, yet locally productive by 2054? The vision behind Fab City goes far beyond just technology or localized manufacturing. It aims to fundamentally reinvent our cities and their relationship to people and nature by relocalizing production so that cities are generative rather than extractive, restorative rather than destructive, and empowering rather than alienating.
So making things locally again instead of shipping everything around the world.
That's a core part of it. Recovering and cultivating the knowledge and capacity for how things are made within our cities, shrinking our dependence on distant, often unsustainable global supply chains. By emphasizing localized production paired with material science innovation and digital fabrication, this movement implicitly reduces reliance on high-impact, globally transported materials.
Which brings us back to concrete, meaning maybe developing local concrete mixes.
Potentially, yes. Perhaps even custom mixes leveraging local aggregates or specific industrial waste streams available nearby. It leads directly to more sustainable concrete solutions and ultimately fosters more resilient, self-sufficient urban environments. It's about harnessing local ingenuity, powered by digital tools, to create a profound and positive impact on a global scale.
If we connect this to the bigger picture, this isn't just about incremental improvements. This represents nothing less than a profound philosophical and practical shift in how we conceive, design, and ultimately build our entire environments.
I agree completely. The ability to design and fabricate locally with digital precision and on-demand capabilities means we can move decisively away from the often inefficient one-size-fits-all solutions that characterize mass production and global supply chains. Instead, we can create hyper-context-specific, highly optimized designs that inherently use fewer resources because they are meticulously tailored exactly to their purpose, their local environmental conditions, and their specific community needs.
So it's not just about reinventing the material concrete, but the whole process of building.
Exactly. It's about fundamentally reinventing the entire process of building itself, making it more responsive, more sustainable, and more democratic. This vision truly echoes figures like Le Corbusier, as noted in Space, Time, and Architecture. He was a pioneer who constantly maintained contact with the rich lessons of the past, while boldly looking to the future, unafraid to challenge conventions. He understood that true innovation doesn't mean discarding history. It means building upon its wisdom with new tools, new insights, and a fresh perspective.
That's a great parallel.
The Fab City movement, in a remarkably similar vein, leverages ancient principles of local resourcefulness and craftsmanship, but supercharges them with cutting-edge digital technology to shape a more equitable and sustainable tomorrow. There's a powerful fusion of old and new. #outro.
We've journeyed through an incredibly compelling story today, haven't we? From the enduring ingenuity of ancient Roman construction techniques, meticulously uncovering Vitruvius's precise mortar recipes, and the surprisingly modern concept of adding burnt brick to enhance performance.
Right back to the very beginning.
All the way to the vibrant, democratizing digital fabrication labs of today. This entire journey, spanning 2 millennia, is united by one absolutely crucial goal: making our most essential building material, concrete, truly fit for a sustainable future.
It's a huge challenge, but there's real progress being made.
We've seen how modern sustainability demands concepts like dematerialization, simply using less material and design for deconstruction, which plans for a building's end of life from the very beginning are driving profound systemic changes in how we think about material impact.
Changing the mindset is key.
And critically, we've explored how cutting-edge digital technologies, from the integrated intelligence of building information modeling, BIM, and the foresight of virtual design and construction, VDC, to the empowering local-first ethos of the global Fab Lab movement, are providing the essential tools. These innovations are allowing us to reinvent not just concrete itself, but the entire construction process, leading us toward creating highly optimized, significantly less material-intensive structures.
Which is exactly what we need.
This ensures that our built world can not only stand strong for generations, but also thrive in true harmony with our planet.
This deep dive truly highlights how deeply interconnected these systems are: materials, design, technology, community. And it raises an important question for you, our listener, to ponder. If we can fundamentally rethink and redesign a material as ancient, ubiquitous, and seemingly unchangeable as concrete, a material we once thought was perhaps beyond significant innovation, what other unbreakable assumptions in our built environment, or indeed in any industry, are ripe for this kind of innovative, sustainable reinvention?
That's a great question to leave people with.
Expanding our horizons of caring, as mentioned in Thinking in Systems, for our materials, for our processes, and ultimately for our environment and future generations, is absolutely key to building a hopeful and genuinely sustainable future for all of us.